Okay, so good morning, everyone. My name is Winam Green. I'm from the Atos Bull Company, and I'm glad to welcome all of you to these sessions dedicated to the presentations of the H2020 Evolve project. For this session, so as you can see in the agenda, we will have 5 talks to present successively an introduction to the project, the hardware and software aspects of the Evolve platform, and then the application of this platform to the different use cases of the project, together with the proof of concept, which are part of the ecosystem built around the Evolve platform. So as we have a very tight schedule, I suggest that we defer all the questions to the end of the sessions. And now, without any further delay, may I invite Jean-Thomas Aquaviva from DDN Storage. He's the leader of R&D teams in DDN Storage, and Jean-Thomas is also the project coordinator of the Evolve project. Jean-Thomas to present us now an overview of the project.
Thanks a lot. Thanks a lot for the introduction. So let's share the screen. Okay, so Evolve project, a 3-year project. So let's see a bit what do we have in terms of consortium and I will say project structure. So it's an ICT 11 project. So this is an initiative which has been funded by Europe 3 years ago. 4 projects were elected. We are one of them. Evolve is pretty large, 19 partners, a total budget of 14 million euros. And the project will be over in 1 month. So it's time for us basically to share the lesson and maybe also to communicate about the results that we get during this long journey. And an important aspect is this is an innovation action. So the purpose is not only to do research and push the boundaries of science, but also to bring some concrete things to the market. On the right, you can see the consortium, and you will see that there is several companies, large and small, some startups and large group, and also some academic institutions. So the consortium is kind of balanced in order to have the right energy in terms of innovation, science, and synergies. So heterogeneous platform to perform convergence between big data, HPC, and cloud. So that's very nice. So here on this slide, you have the 2 aspects of it. You have the conceptual view on the left, and on the right, this is the real thing. So the system that we have built during the project. So obviously for the project of this size, we need to have some real things where you can run application. So this system is hosted at Bull facility close to Paris, and we are running application on a daily basis. There is a team of sysadmin to help the end user. So it's a real functional HPC system. So on the left part, we can see the architecture, at least a sketch of it. So heterogeneity is mostly at the compute side. So this is on the left where you have these yellow boxes. So yellow box means CPU or processing element. On the top, you have CPU plus GPU. So the green array is a GPU. So it's very classic heterogeneous system. So it's an accelerator. On the bottom, it's a bit more original since the acceleration is not a GPU, but an FPGA. So we have some nice example in the project where FPGA can bring a lot of acceleration, specifically for image processing and signal processing. And on the extreme left, you will see that some of the CPUs, they have also this little graphic like a database. So this is basically system which has been extended, augmented with a local storage. So we open the compute node and we insert a fast NVMe directly on the PCI bus. So it means that to store data, read or write, the CPU does not need to go to the network, but can act locally and completely individually. So this is a local storage. So it's also a way to accelerate and to provide heterogeneity. The only thing which is homogeneous in this system is a network. So it's a full fat tree InfiniBand system. And in respect of the storage, there is, so as I mentioned, the local storage for a subset of nodes, but there is also two different tiers. One tier is a burst buffer, so it's a full flash system. We have 8 servers, all full of 24 flash system. So they provide fast results, specifically good for low I/O, small I/O, and things like that. But for large capacities, then we move to the second tier, which is based on hard drive, and it's more for capacity. So we have heterogeneity on both axes, compute and data. So obviously, if we have heterogeneities from the hardware part, we have also heterogeneity on the software side, and this is somehow one of the key aspects of this project. So this slide is coming from the BDEC. So thanks BDEC for allowing me to present this slide. On here, what we do see is that this is a software stack from HPC and big data. And even if they share the same ground, so it's a Linux system, actually these two software stack has been built in a completely orthogonal way. So for HPC, there is Linux, resource management, numerical libraries on MPI on the application. On the big data world, there is more abstraction layer, mostly because they are dealing with commodity hardware. So for instance, on the top of the operating system, you will start with a virtualization layer, such as containers, and then another virtualization layer. So HDFS basically virtualize the file system. And then we have middleware, and then at the very top, we have the application. So if we want to run HPC application on our system and similarly big data, then we need to be able to, we do not want to rewrite everything from scratch, right? So we want to connect the boxes. So we spend a lot of time to build connectors and bridges across these boxes. And one example that we have is that you can run your application on Spark, but Spark will run almost natively on the burst buffer, so with a very high performance. And it's transparent for the end user. It's not aware that it's using burst buffer. It's just a Spark application. So in terms of use cases, we have two big corpus of use cases. So a total of 8 applications. 3 of them are about satellite images. So it's linked to the Copernicus project. And we have Cibeltech, which are analyzing satellite images in order to optimize agriculture production. So they can detect if the crop is growing correctly or not. We have Thales Alenia Space, so they are looking at the same area with different pictures across time, and they can detect changes on the ground thanks to their AI pipeline. Space Helas is also using satellite images, but it's fusion with other information, so there is correlation between the images and the signal sent by the vessel and by the sea. So they need to send their position to the port or to the authority. So we can check here if the position of the vessel is matching with the declaration of the vessel. So it's a very important thing in order to predict the trajectory and also to enforce basically border control in Europe. The second set of application is related to mobility. So mobility is mostly personal mobility, so cars. So here we have 4 different applications: predictive maintenance for the engine. We have also the next step is basically maintenance for the engine. So if we do not predict correctly, we have to fix it. And depending on the car model and the nature of the problem, then an AI system from Kula, so it's a cool startup from Sarajevo, they can help and ease the maintenance. BMW, they are producing the core algorithm for ride-hailing algorithm. Virtual vehicle is working on an autonomous driving application. On the other side of the mobility part in Evolve is maybe a bit more, how to say this, eco-friendly. So it's about mass transportation. So we have a public operator from a fleet of bus in the northern part of Italy. And they are working jointly with IT specialists. And the idea is to use the Evolve platform in order to improve the service and to react to hazard. And when you have a large fleet of buses, this is not a trivial task. So additionally to this application, we have another layer, another way to assess the quality of the platform quality, not only in terms of hardware and software, but do we deliver the easiness of utilization? This is a POC. So the issue that we had with the pilot app is that we embed this application at the very beginning of the project. So basically, we are growing together. So hardware, software, middleware, and the application, and there is a kind of co-design. So we get along and we know each other better, and then we improve the things together. That's very nice, but then sometimes the market is a bit more harsh. And this is why we have this notion of proof of concept. Arrive at midterm of the project when the platform is stabilized enough. Then we go and reach out for external user and we propose them to basically to test and try the platform with their own application. So for us, it's a much, I will say, a better reality check. So then we can assess, do we deliver what we are supposed to deliver? Is it not too complicated for external partner and things like that? So the application heterogeneity, so for some of these applications that we start with at the original, it was like just a big piece of monolithic logic. And now at the end of the project, and this is the way that we have basically enforced convergence and heterogeneity, everything is split in workflow. So this is a modern way of doing computation nowadays. So you have different components which are interlinked all together with microservices. And because this component has very specific process, they are going to put the pressure on a different part of the system. So for instance, in my pipeline, if I'm doing simulation, numerical simulation to assess that the growth of the crop is correct based on my model, then I need a lot of floating point numbers. So it's going to be CPU intensive. And then once the result has been produced by the simulator, I want to have some rendering and visualization part of the result. And this workflow stage is going to use massively the GPU. So this way we have a more complex resource management for sure, but then we have a much better efficiency on time to result. So now that we're almost at the end of the project, what is the bottom line? So basically it works, right? So when you inject accelerator into a platform, well, it accelerates, and we have some very nice speed up, so up to 100. But the important point here is that it's not only about you throw more hardware and then you get faster time to result, is that you improve the whole cycle. And in the cycle, there is the end user, there is a developer, and there is the DevOps. So it's also about boosting the productivity. And the large part of Evolve has been to conceal basically the complexity of the system and to provide the right balance between abstraction and accuracy in order to help the end user with few lines of code to express his workflow, but just with enough information so the resource manager can dispatch the stage on the right part of the system. So it's an innovation action. So it's not only about building a very nice HPC grade converged system, but it's also about putting some innovation to the market. So in Evolve, we have produced 12 different innovations. So they do not have all the same level of maturity, but some of them are on the market actually. So I'm going to detail 4 cases, so not the 12, be quiet. So one very nice innovation that we had, DataShim. So it's coming from IBM and it's open source. So it's already quite a result. And this open source project has been selected and hosted by the Linux Foundation. So it's kind of recognition about the quality of the work. And here the idea is to abstract the location of the dataset for a container. So using DataShim, if I move my container, the dataset is going to move to the right node transparently. We have also use this DataShim innovation jointly with MemoPort. It's coming from a Norwegian startup, MemoScale, the partner of the project. And here the idea, same core idea to try to hide the complexity, is that there is a transparent compression between the S3. So you think about like AWS, for instance, S3 server and the S3 client. And if both are running MemPort, then all the data are going to be compressed, and with a very good compression ratio, because the algorithm has been tuned for satellite images. So we can compress up to 60%. So if you consider that downloading data you have to pay on Amazon, then you pay less, then you use less bandwidth, and you have a better time to get your data. So it's a very nice innovation as well. Earth observer is coming from Thales Alenia Space. So this is a ground detection, excuse me, the change detection
Jean-Thomas, 1 minute.
pipeline. Okay, good. And then we have also a visualization algorithm that is used in a very large US government website. So we are very proud of it. So it's not only about innovation, we have also a good throughput in terms of scientific paper. So almost 1 paper per month, so 36 conference paper, some of them in very selective venues, such as Unix. And as we are open source project, we put something like 100,000 lines of code on GitHub. So now this last slide is basically to introduce the next speaker. So what are the challenges that we had to address in the project? It's very easy to do the introduction, but we had some difficulties to solve, right? So the first one, this is the hardware part. So putting things, heterogeneity into the hardware, it's nice, but then you have to provide a unified memory address space, and it's becoming a bit more complicated. Then the software that I've detailed a bit. So how do we conceal the complexity of the hardware platform in order to allow the convergence between big data, HPC, and cloud? And also, I think this is even the most important part in the project is that how do we validate the result? So and we validate, as I mentioned earlier, with 2 ways. So the full-blown pilot application from day 1 up to month 36, and also this proof of concept where we have basically inject 16 different applications to the platform to assess that it's working as we expect and that we are delivering meaningful result to the market. So thanks a lot. And now I let the stage to Nam for the hardware part.
No, I'm sorry, we cannot hear you.
Okay, I'm sorry. There is some technical problems with my. Do you hear me now?
Yes, we do.
Okay, thank you. Sorry again. So I try to go faster in order to catch up the delay. So I will start with the first slides in order to say about the motivation and objectives in the design of the hardware for the Evolve platform. So our main motivations is to investigate the integrations of hardware accelerations in order to not in terms of computing, but also in terms of data transfers, and in order to be able to support flexible, scalable, and interoperable exploitations of those hardware accelerators for the benefits of the applications, which is the convergence between the HPC, big data, and AI. And obviously, to validate all our developments on the use case proposed within the projects. So the main technical challenges we have to face in our work is to provide a scalable approach to heterogeneous computing technologies, to make the convergence between the different acceleration software, and also the convergence between HPC, big data, and AI, the expansions of HPC scope to the cloud and edge computing, and all of other stuff, while maintaining the native characteristics of HPCs, which are availabilities, reliabilities, accessibilities, and securities. So I will now detail rapidly all the components of the hardware platform, and starting with the computing technologies and starting with the CPUs. During those 3 years, the CPUs have evolved through different families of CPUs from Intel, both were Haswell and Skylake. And the characteristic is that all those CPUs have in common is they are homogeneous NUMA multi-core CPUs. And the other characteristic from one family to another family is that they vary in terms of cores or frequencies. But the main point is that the performance we can obtain from those CPUs are not only based on those criterions of the cores of frequencies, but also to have taken into account the protocols, the different versions of the protocol of cache currents and memory consistencies, the size of the compute nodes, and the presence or not of node controllers in order to expand the protocols to larger size, and obviously the NUMA factor. And another things to be taken into account in the usage of CPUs in order to obtain the maximums of performance from them is the mixing of different programming models for the CPUs, which are today MPI and OpenMP respectively for the distributed and shared memories. And to do that in an optimal way, we have to take into account the system architectures, other criterions like load balancing, memory management, size of a message, NUMA factors, synchronizations of the message, all the stuff, make it more complex to obtain real optimal performance from the CPUs than just to compile it and using default values. So what would I like to point out in this slide is that today, in fact, the exploitations of the CPUs is still rather suboptimal when we look at the different existing implementations of the applications. The next computing technologies is obviously GPUs, which become very common now in different HPC systems and in our platform. And during those 3 years, we have implemented GPUs varying from NVIDIA K20, P40, and now B100 versions of the GPUs. And as for the CPUs, the performance of those GPUs are computed as factors of the number of cores and frequency. But from our point of view, the main criterions which can have a big influence in the performance obtained from those GPUs, the memory type, its size, boundaries, and repartitions in terms of local memories, in terms of shared memories, in terms of global memories within the GPUs, and also the programming models used in order to program those GPUs from high levels or frameworks like TensorFlow, MATLAB, or low-level programming models like CUDA or OpenCL. Another point which is important also is that how to make the interactions between the GPUs and CPUs more performant as possible by merging between the MPI, OpenMP programming models of the CPUs together with the CUDA and OpenCL, and to make the GPUs usage of the CPUs scalable and in terms of mapping of MPI tasks to GPUs, in terms of scaling the code into multiple GPUs and multiplying the GPUs in the heterogeneous cluster. As shown in the figures on the right-hand side, the way that we can merge together different programming models between CPU and GPUs can be used in here in different layers of message passing and shared memories access to each compute node and how use the GPUs within each compute node. The figures on the bottom side is to illustrate how we can optimize the access of the memories from GPUs to GPUs or to the CPUs memories or from GPUs memory directly to the equivalent networks to communicate with other compute nodes. This slide is just here rapidly to illustrate some of our purpose. For example, on the upper left, right side of the slide, you can see some figures, some results obtained from FFT applications. It demonstrates many things. First of all, when we use GPUs, for example, when using CUDA, which is a proprietary programming models against standard programming models like OpenACC, for example, most of the time you obtain better performance than the open standard. It is somehow rather the natural due to the fact that it is a proprietary from NVIDIA. And there's also the performance is some kind of a trade-off between the transfer of data and the executions on the cores of the GPUs. And somehow for this kind of application, we can see that very significant speed up against the CPUs. On the two figures on the bottom of the slide, what is illustrated is that when you combine together the OpenMP together with MPI, we have a very big variations in terms of performance, but also in terms of footprint of the memory. So it depends on what is the criterion we are looking for. We have to, let's say, combine those programming models in a way or another way. Now let's go to the FPGA rapidly. FPGA is a very old technology, it's older than GPUs, but it is not yet very well used and considered in the for the applications due to the fact that it deals mainly with hardware considerations. Today, the characterizations of FPGAs are in terms of CLBs, of logical elements, in terms of LUTs, embedded RAM, DSPs, interconnect, or SerDes transceivers, which are not well known by the applications, software applications developers. And the FPGA-based programming models today offered only two alternatives, either directly using HDL, like a VHDL or System Verilog, or using OpenCL. And OpenCL, the way of approaching OpenCL with FPGA is illustrated by these figures in here. On one hand side, we have the compilations using the software part, and on the other side, the kernels is synthesized and mapped onto the FPGA. And on the right-hand side, we have the stack of all necessary software in order to support these implementations of OpenCL for the FPGA. And what we like to say also is that in terms of FPGA, the FPGA is technologies, is programming technologies compared to the more oriented processors like GPUs, for example. So we have a lot of flexibilities to implement the different features. And one of the features we have intent at the beginning to implement on our approach to FPGAs is to allow it with the abilities to access in a cache coherence and memory consistent to the memories of the CPUs. And this is by using some of the features provided by Intel for their SKU technologies. That means that the abilities to connect the FPGAs directly to the CPUs onto the same sockets using the protocol QPI protocol. And in here, normally, with that, from the FPGAs, we can access directly to the memories of the CPUs in a cache coherence manners. And this FPGA itself can be extended using HSSI connectors to other FPGAs in order to implement larger applications. But after that, Intel have dropped off this approach. Today, our solutions retain for the evolved platforms is only the connections between the CPUs and the FPGAs using the standard HPC Express. But they still remain with the abilities to extend this kind of approach with larger FPGAs, more FPGAs using that other either the directly HSSI or other kind of interconnection between the FPGA. So these figures in here in order to illustrate rapidly how we can interconnect the different acceleration technologies together. We have the CPUs communicating through the protocol, current protocol, which can connect it to GPUs and FPGA at the same time, so we can combine all those technologies together. Today we have used NVIDIA V100 as GPUs and static stands as FPGAs in our compute nodes. So now go into the next component of the HPC cluster. There's 3 points I would like to point out from this slide. Is that in our design of the compute nodes, we use these formulas of HPC benchmarks in order to size the memories of the compute nodes in order to be able to fit into different type of applications. That means that 2 GB per core. Another point, as already said by Jean-Thomas previously, is that we introduce the bus buffer exemplified by the DDN's IME technologies in order to accelerate the accelerations from the compute nodes to the storage device. And the third main point is that we also allow to add local storage to compute nodes in order to accelerate some workflows which needs local storage in order instead of going to down all the networks to the storage device.
So Nam, maybe in 2 minutes.
Yes, I will go fast. So the third components of HPC clusters will be the Interconnect Fabric. And for this Interconnect Fabric, just to say that for the hardware platform, there's in fact 3 different networks, 2 InfiniBand. First one is to connect compute nodes together. Second one is to compute the compute nodes to the bus buffer and storage device, and Ethernet networks in order to connect the management nodes to the rest of this design. So here is again rapidly the architectures of the platform. We have compute nodes in here. We have a storage device on the right hand side, connecting different bus buffer together with the loose nodes for the storage. And we have the management nodes to communicate with the outside worlds, connecting together with all the other nodes. So we have all the illustrations on the right hand side. So now I come to the conclusions in order to say it again, what are the main points of our contributions in terms of hardware design to the Evolve platform. We have investigated some aspect of the general purpose computing accelerations, including GPUs and FPGAs, and we also consider the restructuration of the memory storage hierarchy by introducing bus buffer, but also by starting to investigate some other features like data compressions at some nodes. And the main point is that in order to obtain real benefits from these architectures, we have addressed the problems of co-design. That means how to work on the application on hand side in order to map it in the most optimal way on those architectures of the platform. Future of the developments will be accelerations, but more oriented to specific applications like AI applications, in situ computations. That means providing computations on some local nodes like storage nodes, for example. Co-designs once again regarding all those new features, new developments, and obviously the evolutions of HPC towards the more open HPC cloud edge continuum. That's all from my side, and I'm now glad to introduce the next speakers, who will be Professor Angelos Bilas from the University of Crete, and who will present now the software part of the Evolve platform. Angelos, it's yours.
Great, thank you very much, Nam. Let me share my screen and the slides. I believe this is it, and you should be able to see in full screen. So my name is Angelos Bilas. I'm with Fourth, and I will give an overview of the software stack in Evolve. So Evolve is a project at the crossroads of big data, cloud, and HPC, as was already mentioned. The goal and scope of Evolve has been to process large data sets and to do so interactively for user-facing applications. Now, if I am sort of to give the main and the distinctive feature, right, in each of these 3 words, big data, cloud, and HPC, I would say that big data has always been about productivity. The goal has been to decouple users from the platform and allow them to process a lot of data with reduced effort. The cloud has always been about optimizing resource cost. It has been driven by consolidation, resource provisioning, shared use of resources that ultimately aim to reduce cost. And HPC has always been about performance, striving for vertical integration and using advanced storage interconnects and accelerators. So the hardware platform in Evolve has HPC features, as was discussed in Nam's presentation. And for the purpose of the software stack, we can sort of abstract this platform with the following aspects. It has substantial heterogeneity. It is of substantial size, hundreds of threads in large multi-core servers and substantial memory. It uses fast interconnect InfiniBand, in fact, with RDMA support, and then different generations and types of accelerators, both GPUs and FPGAs. And I'm not sure, maybe, okay, this is great. On the storage side as well, there is substantial heterogeneity. There is the Infinity Memory Engine, which is used as a burst buffer. This is high throughput storage. There is local storage devices that offer high IOPS, and then there is external archival storage for end results. So I will now go over the software stack in two parts, the front end and the back end. The front end of Evolve is basically, we place this under an Evolve dashboard, which is the front end for all users in the platform. The goal is to decouple users from the complexity of the hardware and the software, the underlying hardware and software stack. It offers secure and private user management via isolated namespaces. It integrates all Evolve and third-party services, and this is done with a container-based management sort of approach, which has proven very fruitful. It has been significant integration effort to provide this dashboard, but in the end, as we have seen from applications and proof of concepts, this effort has paid significant results. The main abstraction offered by the front end is a notebook abstraction, where users, they can essentially provide, they can program their own workflows. We chose Zeppelin for this purpose, but they can also make extensive use of shared templates. The platform includes a custom interpreter for workflows, but you can find more about this in deliverables and publications, right? I'm not going to sort of discuss this in more detail. Evolve workflows in the project, in the end, they are an end-to-end synthetic description of computation for us. Workflows are important for two reasons. It is what the users care about. Users, they want generally to describe an end-to-end process, and they care more about, getting the whole result in the end rather than focusing on a single stage. But also workflows are important for the system because it allows more room to optimize execution, because the system has an end-to-end view of what it needs to do. Figuratively, a workflow in Evolve looks something like this. Initially, you may want to open a data set, then you perform some pre-processing on this data set. Afterwards, you may train a model based on the data, then you perform a simulation of some phenomenon, right, using, let's say, an HPC stage. And then in the end, you post-process the results. And finally, you may want to use visualization to sort of summarize the results to the user. Now, one distinctive feature in Evolve with respect to workflows is that it allows integrating HPC tasks and big data tasks in a single workflow. So workflows can use MPI stages. MPI can also be used interactively from notebooks in Evolve. MPI tasks are able to use GPUs and InfiniBand via containers. So we have extended containers for this purpose. And then Evolve automatically creates the environment where it will execute these MPI tasks. We call this virtual cluster. This environment, it allocates resources to each MPI task along with big data tasks, and I will say a little bit about this later on. And then cooperatively, it executes the MPI tasks under Slarm and Kubernetes. And again, I will say a few things about this later on. Finally, the front end includes extensive vertical monitoring in the sense that it provides information about hardware resources, the software stack, and storage I/O, which has been a focus for us. And these monitoring aspects in such a complex platform are extremely important so that both, let's say, the system side and the user side, they can have a view of what is happening in the system. Let me now move to the back end of Evolve. This is mainly the part of the system that is responsible for using the available resources and achieving high efficiency. So the backend in Evolve has, let's say, three main aspects. One is end-to-end integration of microservices with the HPC platform. These microservices, as examples, the microservices include Kafka, Spark, Spark Streaming, TensorFlow, and Keras, MPI, and extensive visualization support. There has been quite a bit of effort in integrating these microservices in the platform and making them available to applications. However, for now, I will consider that these are given, they are running in the platform, and I will focus on the next two aspects of the system. The next one is enhanced storage features and quite advanced resource management. So with respect to storage, Evolve offers a unified storage layer. Storage is important in Evolve because all tasks and jobs communicate with each other via storage. So essentially communication happens via storage-based address space, which offers practically unlimited address space, and datasets can grow significantly. The unified storage layer contains a component DataSim, which was again mentioned earlier, and this abstracts data as data sets. This is, let's say, a control aspect of the backend, where users see names for data sets without having to worry about where this data are stored or what their format is. And they are visible everywhere in the system and throughout the lifetime of jobs across both tasks and nodes in the platform. The second aspect of the unified storage layer is a device-independent method to access data. This is H3, it's a data access layer, and it offers access to data whether they are stored in local devices, shared storage, or even archival storage. The idea is that H3 provides applications, tasks, and workflows the ability to store transient results on fast local storage, and also persistent end results, let's say, to archival storage, such as Lustre. Moving forward, the resource allocation in Evolve is based on microservices, containers, and Kubernetes, which has proven a very fruitful approach. There are two distinguished and quite advanced features. One is that Evolve performs mixed resource allocation for HPC and big data tasks, workloads, and also users can request information, let's say, performance target that rather than requesting only specific resources. So workflows, executing workflows within in Evolve, this happens in a cooperative scheme under Kubernetes and Slarm. In our approach, Kubernetes is used as the master, although other approaches do exist. So Kubernetes has a full view and of resource allocation in the system. We can support executing full Slarm scripts as MPI job, so this is pretty generic. The users can issue tasks to the system as complete Slarm scripts. Then Kubernetes creates the virtual environments for executing each of these tasks and starts a Slarm subsystem, a Slarm in the virtual cluster, and the two of them, Slarm and Kubernetes, cooperate for allocating the actual resources. We have been executing mixed HPC and big data workloads over the last few months, and the results are indeed quite interesting. About resource allocation, the second significant aspect is that Evolve automatically allocates resources in the following sense. Big data workloads tend to be elastic, and despite this fact, users today need to determine the resources that will be allocated to each task in the system. This is very challenging for users, and it leads to over-provisioning. Evolve instead asks users to specify a performance target, for instance, target throughput. Then after that, the system takes care of resource allocation, so it maps the performance to required resources. allocates these resources and adjusts them at runtime. And this is sort of implemented in the system as a custom scheduler within Kubernetes. This adjustment now of resources is based on an online performance model that our scheduler builds for every application. This model or the approach that we use is agnostic to the application type. And in fact, it can even cope with multiple resource types, CPU, memory, and IO as well. So having provided the information about the front end and the back end, right? If this sounds interesting, please go ahead and try out the platform. There are different ways to do this. So we have get in touch because we have started already to discuss deployment of the platform in specific applications. One of them is satellite image processing, where there is significant need both for data storage, right, and computation. There's a possibility to access the combined hardware and software platform at Atos for third parties. So if this is interesting, again, please get in touch. The platform is available as a cloud version, which you can download and use either on a public or a private cloud. However, this version of the platform does not include the hardware, the HPC hardware support features, because these are not generic features that you can find everywhere. And finally, most components in the platform are already available as open components. So you can download them and try to integrate them in your own platform or even extend them. And in any case, anywhere we can offer help, we are more than glad to help with the platform. Thank you very much for your attention. I'd be happy to answer any questions now at the end of this session or even later on via email. Nam, the floor is back to you.
Thank you very much, Angelos. I will introduce the next speaker, who will be Vasilis Spitadakis. Vasilis is R&D manager from Neurocom, and Vasilis will present now the different use case of the Evolve project. Vasilis, the floor is yours.
Thank you, Nam. Hello, everybody. I will present you briefly the 7 use cases that were adapted into the Evolve platform and their main achievements through this adaptation. As already mentioned, we have 7 use cases, 7 real business case scenarios from different areas. First has to do with change detection satellite images, maritime surveillance, optimizing accurate production yield, predictive maintenance for vehicles and public transport operations planning, data-driven vehicle engineering process, and demand mobility services. All these use cases are using the same platform, the same cluster, exploiting various different microservices, each one to satisfy its different, its diverse requirements in terms of volumes, in terms of rates, in terms of calculations. So the main goal out of this adaptation was, of course, performance. But apart from this, we wanted and we identified flexibility that is necessary in order to conclude such adaptation that is necessary to move a conventional, let's say, application to a new era where you need to exploit HPC, you need to exploit big data frameworks, you need to move things up to the cloud. The main work that has been focused, that has been made throughout this adaptation is containerization of calculations, parallelization, scheduling, and visualization. So we utilized Kafka for data ingest microservice, TensorFlow. We utilized GPUs, MPI, Dask for scheduling, Spark streaming for stream processing, and at the visualization stage, we had also the Web Lizard technology component which was integrated also within Evolve. Let's start with the change detection application. It is an Earth observatory application where you need to get images from the same area at consecutive time windows, let's say, which need to be compared, and finally you need to identify and produce a new image that identifies the changes that are being observed. So it's a very interesting and very important application nowadays, because many different applications and business domains are relying on change detection. And such kind of multi-temporal change detection is needing fast access storage for a big amount of data, and computational intensive processing in order to identify these changes, and in order to be able to process larger areas in more quickly. So for Thales Alenia, which is actually the business owner, the objective of this pilot consisted in detecting changes over the entire Europe during 1 year, with a revisit period of 10 days. So this application required to access and process about 35,000 tiles, which is about 20 terabytes of storage of data coming from Sentinel-2. The main steps were including the downloading of Sentinel of the Sentinel data product from the Copernicus Access platform, processing each Sentinel data product in a single image with a bunch of items, and finally having 2 time consecutive images of the same field of view being generated. The last step is to compute the change detection map between these two. So what we did, what Thales Alenia did, it utilized parallelization frameworks, the stream analytic engine, fast storage, and hardware accelerators in order to automate, optimize, and boost the performance of the change detection tool. Actually, for this use case, we also explored different variations of the platform, using also the task scheduler, which has been deployed for parallel computing inside the modules. And the module with the artificial intelligence algorithm has been rewritten in pure TensorFlow to take advantage of the GPU accelerators, as well as it was ported using OpenCL to FPGAs, so that to compare the performance using the HPC features of the platform. All stages were containerized. Communication was done using Kafka topics. And finally, we made experiments with 8 different variations of the platform. And we experienced 10 times faster average time for generation of one change detection map from a couple of Sentinel-2 images running on CPU and task. While when we brought also the GPU, we moved from 10 times faster to 15 times faster. And what was actually more interesting for us and for Thales Alenia is that we experimented on a big data environment where we work with 200 Sentinel-2 images, where we get using the CPU, not the GPU, but the task version of the platform, of the setup, we got 120 times faster conclusion of the whole process. More information can be got from Thales Alenia about this use case. We can move on to the next use case, which is about maritime surveillance, a very important application for maritime safety, from transport, for monitoring and identifying illegal immigration. Here, the business owner is SpaceLas, a company from Greece. And the stages here of the processing are including data acquisition of 2 different types of images. The first one is getting images for SAR, radar images, monitoring the seas, as well as getting data from the AIS system for the automatic identification system of vessels. And you need to correlate these two in order to identify whether there are some abnormal, let's say, moves. And so we have data acquisition from these 2 sources, anomaly detection run on the AIS data, image filtering and processing of the radar images, vessel detection, and fusion correlation between these 2 sources, and finally, visualization over a map GIS interface. All stages were deployed in the platform. They utilize the Zeppelin, the vol-specific Zeppelin notebook facility. And the main work was to transform the existing pipeline to the evolved logic, which included the engineering of the workflow and containerization of all stages, with the aim of taking advantage of the accelerations, of the evolved accelerations, mainly the parallelization of the IME fast storage facility and the hardware accelerated distributed processing. Dedicated attestation modules were developed for both the AIS data and the radar images, and all the processing stage was achieved natively within Zeppelin. Having evaluated the deployment in Evolve, we got out vessel detection time we reduced the time for vessel detection by 70%. 89% for anomaly detection we reduced the anomaly detection, the training time of the anomaly detection model data. The accuracy has increased by 5%, while we managed to increase the time spatial window, which is very important in order to be quickly into responding into such requests for monitoring a specific area. Comparing with the previous situation, in absolute numbers, this means for vessel detection now we can do it in less than 1 second, while before Evolve we were doing it in about 3 to 4 minutes. Anomaly detection was needing 8 hours to train the model. Now 2 hours are more than enough for the training phase. Data-driven vehicle support is another use case. Here we are mainly dealing, this is a computational intensive application that it is mainly executing time series analysis for anomaly detection over a time series data, which are monitoring the data, the pressure of a cylinder in an engine, which combined with other engine operation data can identify areas, points in time where abnormal situations need to be considered. So we have to find patterns and correlate them to numerous other patterns that characterize normal behaviors, so that a specific pattern can be classified as normal or problematic. AVL from Austria is the business owner here. They have already a system doing this called EPOS, working with the cylinder data, very well optimized for the environment in Windows. AVL managed to reduce by 40 to 50% the overall workflow execution time. The main work that has been done was, okay, they containerized and uploaded it to the Evolve platform. They use profiling in order to optimize the code. They changed the file format to Parquet, which allowed to take advantage of parallelization. So it was mainly the parallelization that pushed that was exploited, while the experimentation with the GPU didn't reveal so great performance improvement, because actually it was applied to a specific processing stage which was consuming just 1% of the overall calculation time. Public transport the public transport operations of Thieme, a Toscan a bus operator in the area of Tuscany in Italy, brought their data into the Evolve platform. Their data was mainly about bus events, schedules, and the network, the actual network. And we implemented 2 different workflows. One was a batch workflow dealing with getting data about the actual performance that is monitored over the transport network, and comparing it to the schedule, to the promised, let's say, operation, which is a very important decision support tool for the operation of the authority. The need there was to expand, to make the queries faster, and to expand the time window where you base such decision. And the second workflow was a real-time workflow which was not existed before. And now it made possible, it was possible through the Evolve platform. Both workflows utilize the Kafka ingest microservice. They utilize the Argo events for scheduling, and Spark, as well as Spark streaming for the real-time case. Two different visualization stages were exploited. In the batch workflow, we integrate their existing business intelligence application through the Spark thrift server, so that to exploit the Spark query engine results and visualize them on the existing application. While for the real-time workflow, where you need to identify congestion, the congestion on the network at the time it happens and correlate it with the bus event data that we are getting, we utilized the visualization component that is being integrated within the Evolve platform with the Web Lizard technology. Here we got also important, very useful, very good performance results. Mainly, there are some daily queries which are applying on a daily basis within a period of interest for 30, 60, 90 days of service, where you need to get a summary of the transit time analysis. And this query gets from 2 minutes up to half an hour when you are making this query of over 90 days. Now we need just a few seconds, 60 seconds for 90 days and 11 seconds for 30 days to get this query done. Very important achievement is that before Evolve, the operator was working with 1 month data in order to take decisions, data from 220 bus seats. Now, 1 year data can be processed across the whole area of Toscan. And last but not least, okay, we didn't have any past experience from real-time visualization from the network, but now we got, and actually now we have the experience through Evolve, and now we can be able to visualize 2 or 3 selected lines of routes within 6 seconds, as well as we can process more than 20,000 arcs in the transport network in under 20 seconds. Another application has to do with active production optimization. This is very important.
Please, 1 minute. 1 minute.
This has to do with the monitoring of agricultural parcels, where you need to identify the crops cultivated, and you need also to simulate the growth in respect to the climate and environment and the farming practices that are being applied, as well as the environment conditions. This is a very demanding application dealing with numerical processing, with vast data of numerical processing with and great complexity. Here we utilized MPI, especially for the simulation process. Everything again was containerized, and we managed to get an increase of from 90% to 97% in respect to the success rate of crop detection. While the most important achievement is that we Cipetec, which is the business owner, managed to multiply the dataset size, the area, by 5 times. Predictive maintenance is another use case, another business case. Here, here we got again data, engine data from vehicles, which data from warranty repairs with current vehicle sensor data. Here again we used R, Python, TensorFlow, and MongoDB. We apply logistic regression, linear discriminant analysis, classification regression trees, and SVM. And finally, we got a speed up of within 2 and 3 times speed up in the overall preparation, training, and serving of these data models. We are also now measuring the speed up with using the GPUs. Finally, we have the demand mobility services, the business case of BMW, where we have the problem of ride hailing. So you have a network of a share of cars that are within a city, and you have requests coming from people who want to move from one place to the other. Again, you need to optimize the way to which car will serve which request and at which time. The business case actually has to do with the research that BMW is doing on the various algorithms. So with Evolve, all these simulations were done over a larger amount of data sets that were actually covering the New York, let's say, taxis, the fleet of taxis, and we got significant acceleration as well as significant increase of the problem size that is being investigated. To conclude, we were expecting that we were expecting remarkable performance improvement because for most of the use cases we are moving to parallelization, we are moving to GPUs, we are moving calculations to FPGAs, to efficient storage and efficient compressions and efficient visualization. However, I stress again that the most important achievement, the most important conclusion out of this experiment was that use cases managed to increase the quality and quantity of business indications, larger areas, more accurate results, while on the same time they got development efficiency. Experimenting with HPC, with different components of the platform was now more easy. The dashboard, the Zeppelin notebook, or all these scheduling tools and upon the containerized stages of calculations made their life easier to our new data pipelines, quicker data pipelines, and easier to manage them and edit them and re-engineer them. Thank you for your attendance, and I will pass now the floor to Alexander, who can tell us about the proof of concepts, which were, let's say, some more use cases that were added into our experiments.
Okay, thank you very much, Vasilis. I introduce rapidly Alexander. Alexander Stokers is a project manager at Virtual Vehicle Research GmbH, and he will present to us now the proof of concept for the Evolve project. Alex, it's your turn now.
Thank you very much, Nam. I'm trying to share my screen. So I hope you can see my screen now.
Yes.
Yes.
Well, you have already seen from Vasilis 7 official project use cases that have been implemented in the project runtime. I would like to now draw your interest on our proof of concept experimentation or implementations. You can see proof of concepts somehow as a smaller mini use case that were identified during the project and involved also externals that can be external partners like external companies that implemented workflows on the testbed using the support of the consortium partners, but can also be partners from the consortium members, but external to the core team that implemented workflows. In proof of concepts, you can have two variations. The first is a variation in data sets, so different data sets than in the pilots, but also a variation in the application context, so different application context. We have in total implemented 16 POCs on the testbed, and you have on my slides, there is a list of POCs. I won't go into detail in all of them. Don't worry, that we would need much more time for this, but I would like just to give you some overview on the application context. So we have a POC on vehicle monitoring, but also on sensor measurements. But we then also have other application domains like genetics or genotype imputation. So biology also as an application domain that was addressed in POCs by Forth. We have further image processing POCs. We have for the bus service use case that you have seen, we have also two POCs. One is on a bus fleet monitoring from a different city, and the other one is on traffic congestion, but also using data from a different city to show the generalizability of the workflows that have been developed. We have one POC also in the domain of retail and retail AI. This is especially really cool because the implementation here was done by an external company, by a French startup, XXII. They do in-shop monitoring using neural networks, and this was done together with DDN, but most of the implementation they really did by themselves, which is super cool for a European research project, I would say. We have two more POCs on crop grape simulation and also on the recognition of field boundaries for crop fields. We have, so here in agriculture POCs, we have POCs on network security analysis, so cyber security, security incident detection. We have DNA, RNA sequencing, we have particle simulation, so we also address physics as a domain. And we also have another application-oriented POC working on telecom usage data to predict churn. Finally, to finalize with the list of POCs, we have one of driver monitoring, which I would like to go in a little bit more detail, and another one on object detection for automated driving for autonomous vehicle, which is a very up-to-date topic, I would say. I would like to go a little bit into detail in two POCs that were implemented. The first POC I would like to talk about is the status detection of vehicle assistance systems, of autonomous driving systems from video streams of a vehicle dashboard, which is really nice. Why is this useful at all? This is useful when you want to do user experience studies or user experience studies, putting people into an automated vehicle and assess how they interact with the car. I have here a screenshot. This is more or less an image of a vehicle dashboard of such an automated vehicle. In this case, it's from Volkswagen, and you see here some green symbols. The first symbol showing a road, this is green. That means the vehicle was able to identify the road borders and can steer autonomously, so to say. And the right symbols, this is also green. That means the vehicle was able to identify the distance to a vehicle driving in front of it. That would be this yellow symbol. And if you have both activated, you have some feeling of automated driving. So in a driver study, usually you would like to know when the drivers have activated the systems and when the systems work properly, which is not very easy because you do not usually get access to the vehicle campus, to the CPU to get this information automatically. So there is some kind of hack needed, and this hack is recording images of the dashboards with a camera and then applying some sort of image recognition, computer vision technologies to identify the status changes in these images. This is more or less what was done in the proof of concept. So here also, like in the pilots, there was a workflow implemented on Evolve for the detection of the symbol states. It was not machine learning, it was a pattern matching approach. You see here this pattern. So it was explored where this pattern emerged in this video. Of course, there were some tunings like applying GLAI for contrast adaptation to improve the quality of this pattern matching approaches. And the workflow was implemented using OpenCV and using also GPU and CPUs and GPUs. The workflow also used Kubernetes, so Argo. There's the Argo file. It was a directed acyclic graph. So you see here the parallelization of image processing to speed up the performance. This is a video. So you see here this dashboard of a vehicle. It's exactly a driver is using it and it's driving. And you see here a little bit also there are light effects. And you see here the small videos. And in the subtitle file that is loaded to the video, and this is automatically was created. You see here a change from the status in use, activated in use, car in front, and activated in use. So it detected really the symbols correctly. You see here also the screen card, the user interface of Kubernetes, and you see this was done in parallel, the processing to speed up the processing time. So more or less, we experienced, so from porting this workflow from the local environment, from the data science, from the PC of the data scientist, the desktop PC to the Evolve platform, you see here the impressive performance improve 41 times faster when using the GPU and the CPU and the GPU instances in parallel. A second POC I would like to go a bit more into detail is driver distraction, so driver monitoring. You probably know that distracted driving is one of the most common causes for serious road accidents, and this to prevent these road accidents, the driver monitoring systems are needed. And in this proof of concept, the idea was to develop a lightweight driver monitoring solution running on a smartphone of the driver and processing videos, detecting distracted driving on the images, and then warn the driver. So here there are 3 examples of the data set that was used that show distracted driving behavior. So here the driver is like texting with the phone. Here the driver is reaching behind, and here the driver is talking. So these are really examples that were used. And the data set used with all these labeled images was from a challenge on Kaggle. It was the State Farm distracted driving data set. So State Farm is a US insurance company that posted this data set on the Kaggle platform for a challenge. And the data set was used in Evolve really also to train, first of all, a machine learning model that is capable for detecting this distraction classes. So you have 10 classes of distraction on the right side that are in the data set, and also then to deploy this model on a smartphone for having some lightweight driver monitoring system. The data size was for the labeled training data set about 950 megabyte of images, and for the test images more than 3 gigabyte for them 3 gigabyte of image data. Also, I won't go much into detail, but also there was a pre-processing conducted to pre-process the images before finally the action was predicted. The training was done in first in single mode, so without any acceleration on the Evolve platform, using Zeppelin notebook GPU and OpenCV, the Python library for training the machine learning model, but was then later to speed up the performance also done in a distributed way using Cubebox, but also MPI or TensorFlow, more specifically the Horowat framework, which was provided as a service on the platform. This is a framework developed originally by Uber, used for such image classification challenges. Finally, as in the first POC, I think here also the implementers experienced really a huge performance increase in training the neural network, the machine learning model. It's about 15 times faster than in the local environment, but also for predicting the action, so running the model to identify a typical distraction on an image. It's also more than 7 times faster than on the local environment. The accuracy is also pretty good. So overall, there was an accuracy of 98, even more than 98% of identifying the distractions here by using a base model from the literature, but that was not very optimized. That was adapted just to test the Evolve implementation. Maybe for some who are interested, what was the most difficult class to identify? That was obviously here in makeup. That was the hardest type to classify for the neural network. And there was a lot of confusion, as you can see in the confusion matrix of this class, with 2 classes talking to passengers, texting right, and drinking. Finally, when you remember, the overall goal was to really have a driver distraction and detection and warning system. So I've talked a bit about the distraction, but not about the warning. So to also have this, my colleague who did this implementation deployed the TensorFlow Lite model on a smartphone, and to run it on the smartphone with the front camera, and also tested this in a small scale study in a real world setting. And of course, as you probably might also figure out, there is, of course, when you do it in a real world study, there is a much lower reliability of the system due to different camera angles when you have it in the car, and also different light position or light and light effects. So it might obviously need a more, even more comprehensive data set with more different situation to train a very sophisticated model. But that was obviously not the goal of this POC. The goal was really to challenge the Evolve testbed and use as many of the Evolve microservices that are provided as possible. And I think that went pretty fine. So that's it for my talk. I tried to save some time. I hope it was successful, and I'm looking forward to your questions.
Okay, so thank you very much, Alex, and thank you to all speakers of these sessions, Jean-Thomas, Alex, Vasilis, and Angelos. So it's now time to open to questions. Is there any questions from the audience? Okay, so if there is no question from the audience, I suggest something to wrap up our sessions. We have about a little bit more than 6-7 minutes. In my presentations, I already start to say for the hardware design aspect of our Evolve platform, what will be the next step we envision on outside in order to make all things evolve, and particularly for the design of the future architecture for HPC. So I already sketched about implementing more the hardware accelerations, more specific and AI-oriented hardware accelerations, more institute computing, and particularly storage, in storage computing, but also in networks computing. I also talk about more works about the co-design in order to adapt applications to those new features of hardware architectures. And more than this, afterward, to adapt HPC architectures in order to support more efficiently the overall architectures of continuums of cloud and edge computing. So this is the visions on the side of the hardware. I would like to know about your visions on the different other side, on the software side with Angelos, and also you see on the application side together with Vasilis and Alex. And at the end, Jean-Thomas, maybe you can wrap up overviews of the project. So suggest Angelos, you go next.
Very good. Thank you, Nam. So as a reflection in the project, right? The building the software stack has been extremely interesting, and in the end, it was also it paid, right? And the applications were able to use it. One of the things that we have started wondering about is how do we extend this to the edge? So the full platform in Evolve right now is for a platform within the data center, for a hardware setup within the data center. But many of the applications do require, especially new applications, using the edge. And some of the concepts, workflows, managing storage, state, right? These are problems that Evolve does solve, but addressing them for the edge, they introduce significant new challenges. And we believe that this is going to be a next problem for us, and somehow we will need to go in that direction.
Okay, just interrupt before the continue with Vasilis. And there is a question from the audience. The question is how Evolve can be used for dynamic system simulations such as climate or other complex problems. So who would like to answer these questions? I can try first. From the hardware part, obviously, hardware part, when we try to introduce hardware accelerations to our HPC architectures, it is effectively to support the simulations of more complex problems, to be able to handle larger problems, to provide the ability to process the simulations in more parallel way, to access it, and afterward to use a more approach, different kind of approach also to the simulations problems. For example, using AI-based techniques to the simulation problems. So that's why what we are doing in Evolve somehow is not only oriented to what AI applications as maybe giving this kind of feeling during the presentation of different applications, but also to serve also the simulations of complex problems. So, and we continue to work on this in order to provide more abilities to communicate between different computing technologies in order to be able to execute more efficiently different simulations workflows to include the different aspects of simulations, visualizations, debugging, stuff like that. So this is for my part. Who else can add to this answer to this question? Thomas, Angelos, Alex, or Vasilis?
So now I can say, so basically for an application that is coming from the HPC world, right, the hope would be that by using the platform, someone will manage to improve, let's say, productivity. So if you have an end-to-end workflow that describes what you need to do, without too much effort, it should be possible to execute this on the platform, and this should make modifying the whole workflow easier for users, so they can experiment with it, they can create alternatives of the workflow, and we have seen this in some cases in the use cases as well in the project. So coming again from an application, right, that is, or from a workflow that is, let's say, HPC oriented, the bigger gain would be on the productivity side, I think, right?
Thank you, Angelos. Anything else from all that?
I would say now, just to wrap up also in respect to the use cases in general. Well, having dealt with all these different use cases and proof of concepts, we realized that for all of them, now it is very productive how the final results that they're getting, and in terms of performance, and it's very productive now of what they can do onwards with these workflows, because requirements will still grow for them. So one thing is this. Now, concerning their move, starting from the before Evolve situation to the getting on board Evolve, the effort might be different from case to case, because not all use cases are let's say, have already reached an architecture which is very close to workflow logic. So it is very important that for a use case like the one mentioned in the question, like climate simulation of dynamic system simulation of climate conditions, as long as there is a workflow of specific calculation stages with different data sets from state to state, using using some microservices, this makes easier their move onto the Evolve platform and the quick exploiting of the benefits that the platform brings. So this is so to my view, use cases like the one mentioned in the question can be utilized, can be brought on Evolve, and especially dealing with large amounts of data with AI techniques and similar calculations. But it is good it will be more productive if they are already, if they have already structured into workflow-like approach their use case.
Okay, thank you very much, Vasilis. So there is not much time left. So I suggest that Alex, you have 1 minute, and afterward give 1 minute to Jean-Thomas to wrap up the session. Alex, if you have something to say.
Yeah, so looking back to the implementation of the POCs, I think it went quite smoothly. So we were able to identify more POCs than we planned, which is not something that I have seen often in European research projects. Especially our POCs, we had like 4 POCs. We really have this workflow logic that Vasilis mentioned. So for us, really moving them to evolve was not or just used a limited deployment work, which was fine, because then we had more time for testing and improving the algorithms.
Okay, so there is 1 minute left. Jean-Thomas, the floor is yours to wrap up for the project. Jean-Thomas.
Okay, sure. Okay, so just in 1 minute, I think in Evolve we've been pretty successful about optimizing things within the data center. And as you've mentioned, now we have the feelings that, I mean, we're already seeing this trend that it's not cloud, it's multi-cloud. So organizations tend to have their computation data distributed. And then with the edge, it's even more striking. So we see this movement toward, data anywhere where there is data acquisition, and compute everywhere. You move the process close to the data acquisition place. We really see this as the next frontier for Evolve-like project. Within the data center, now we are safe. It's running well.
Thank you very much, Jean-Thomas, for these conclusions. Thank you again, all the presenters for your contributions. Thank you for the audience for your attendance, and I suggest you can join us on the booth if you want to have further discussion together with the partners of the project. And thank you also, obviously, to the organizers of these sessions, Mattia and Petra. Thank you for your help. Bye. Bye-bye. Bye.
Thank you. Bye-bye.